Howdy. Good morning, everybody. Thank y'all for being here. Hope everybody is doing well and having a good Thursday. Per usual, we're going to start with a short quiz. So if you guys wouldn't mind clearing your desks, the only thing you'll need is something to write with. I don't care if you write with pen or pencil, but just make sure we're clearing our desk of everything except for that. Um, yeah. You guys wouldn't mind just taking one, passing it back, and not looking at it until everybody's gotten it. Look it up and take one of it. Yeah. Mhm. Alrighty, y'all are good to go ahead and get it started. So, yes. Oh, sorry about that. Good luck. Give it your best shot. If you have questions about what it's asking, let me know. And when you're done, you can bring it up to me. One more minute. Alrighty, y'all. That's the end of time. If y'all would please make sure you got your name on it, but otherwise pass them up front. Writing should stop unless we're putting their name down.
Are we allowed like circle if we do that in circle on?
Oh yeah, if you didn't circle it, it's fine. I'll be able to figure out where the
Provisional motion. Would you recommend this to study our last? I
didn't talk about it.
Only on. We're gonna find it.
This everybody's.
Okay.
At the end of class, I'll pass back quiz 1. I have those graded, and you should have seen your grade on Canvas. Getting questions about kind of what to study. So that's kind of how I wanted to start the lesson for today. So today we are going to talk about lecture 4. Lecture 4, we're going to continue kind of our discussion from last time, continuing working with the one-group diffusion equation. We're going to be doing mostly applications today. So after I saw the first quiz, I wanted to talk a little bit about just some kind of standard things that I would recommend, but also learning strategies. So a lot of us, whenever I came to grad school, I had to kind of reframe how I was thinking about like, what am I here for? Am I here to just get the PhD, or am I here for something more? And Dr. Kimber kind of had me rethink how I approach this, and that's what is the first line here, which is that all of us are here to get a nuclear engineering degree. When we go out into the real world and you meet somebody and you say, I study nuclear engineering, they're going to say, wow, tell me about Fukushima. Tell me about Chernobyl. What's up with all the waste? So, like, you are going to be expected to have knowledge in this field because of the degree that you have. And as people in nuclear, we need to be able to communicate our information. We need to be able to explain it to people who are experts, but also the general public who has no idea what all of this stuff is about. They're scared of it because they don't understand it. And it's part of our responsibility to know this material well enough that we can explain it to other people. In every class, it's going to build on itself, right? That's like one of the things that's really tough with math, is that if you have gaps in math, they always build up on themselves. When I started at community college, I failed the math TSI test. So the first math class I took in college was elementary algebra. And that's because my math sucked and I had a lot of gaps. But in filling out those gaps, it ended up being good for me because I needed to know those things so I could take calculus and differential equations and all the fun stuff that we need to know so that we can do engineering. So anytime in this class, if you see a symbol like microscopic cross-section, macroscopic cross-section, flux, the fission spectrum, if you see these quantities, we need to be able to provide the name of the quantity. We need to be able to provide the units of the quantity, and that's at the bare minimum. Because if you look at the diffusion equation and you don't know what the units are associated with each symbol, when I tell you that each of these terms is a rate density, you're very confused and you don't know why I'm saying that. But if you know the units of each of those terms and you know what they represent, we can put all of this information together. So the name and the units are really important. The physical definition should agree with that. Like if you define microscopic cross-section and you say it has units of centimeters squared, then your explanation, your physical description of that should say something about a cross-sectional area, right? Because of the units. If you write reaction rate density, that's another good one because the units are actually in the name. It's reactions. It's a reaction rate, so it's reactions per unit time, but then it's a density, so it's reactions per unit time and per unit volume. And if you know the name and you know the units, then you could probably put those together to piece a like plausible definition, a physical explanation for that thing. So if you see a quantity in this class and you don't know about it, we have to do the legwork to make sure that we understand it. Otherwise, we're going to look at this equation and it's going to be like we're looking at a foreign language and not something that is physical and that we can understand if we know all of the individual pieces. So that's like for general quantities and for definitions too, like when I talked about in the first lecture, Doppler broadening. That is a concept. There's not really an equation for it, but that's something that's going to be really important. I haven't asked you about it yet, and we're going to get into it more. But like, so when I'm mentioning stuff in class, especially, going through a procedure by which we make sure that we have this kind of fundamental understanding is good. The Feynman technique is the thing that I would recommend to develop that understanding. And it's a process by which there's basically these 5 steps. If you're trying to learn a new concept like the scalar flux, then you write on the top of the page, understanding the scalar flux. And then the next thing that you do is you try your best to explain that thing in your own words. That would be probably from like looking at the lecture, maybe looking at other notes if like you can't get a good definition. Once you get a definition down, you want to interrogate that definition. You want to read it to yourself. You maybe want to even read it out loud. You want to ask yourself, are the words that I'm speaking make sense? A good way that you can see if it makes sense is you could try to explain it to somebody else. And if you can explain it to somebody else, that's a really good sign that you understand it. But then even after that, you might find ways that you could improve it more. And so that's the revising in simpler terms. And I am still doing this. Like, I don't think that my definitions and my understandings for these terms are complete. I'm constantly trying to revise them and think about them better and try to like have an understanding that I can convey in a better way. So after every lecture, I would recommend doing this if you see something that you don't understand. And then once you've went through the lecture and you feel like you have a solid understanding of what we talked about, starting the homework as soon as you can is going to be the next thing. Because generally, I'm not going to quiz you on something that we haven't covered in lecture. So if we are doing these things, we're going to be staying on top of what we need to do to have the like fundamental understanding. The whole point of the homework is it's the practice. So, and this class goes really fast. Like there's 10 weeks. Every week we're basically covering a whole chapter of Dr. Svetkov's notes. So after this lecture, after this class, we'll basically cover the first 3 chapters. So the summer class comes at us fast. We have to make sure that we're staying on top of our stuff. That's why I highly recommend starting the homework as soon as you can, because after class, you're going to be equipped with the knowledge to be able to at least start the homework and understand it. My idea with the lecture is that I don't have to do the filling in, but I feel like us filling these things in together is helpful so that we're going at it in a kind of slow, more or less step-by-step pace. I'm kind of giving you guys like a scaffolding from which you can build a bigger structure. But that is going to require that we are doing legwork outside of class, specifically making sure that we're doing these kinds of things and then starting the homework as soon as we can. Because like the first quiz was like kind of definitions and concepts. The second quiz was more fundamental math, like it's conservation. And so this differential equation that I had you guys solve, we solved it in the first class. We've seen it in like 3 other lectures. So it's practicing the things that we have already seen. But like, so if I show you guys an equation and I say the solution is this, that's kind of like the teacher giving you a hint, which is that I should be able to go through these steps as the student, right? And if we derive something in class, if I'm taking the time to like show you step by step how to derive something, you better bet that I could ask you that on a test. You should know these things if we cover them in class. So I'm not mad or anything. I hope it doesn't come off like I'm mad. I want everybody to learn and to do well. And so like this is a strategy that helps me, so maybe it will help you. Another thing with the Feynman technique is that after you do this, very easy to take that like Feynman write-up and convert it into a flashcard. I love flashcards. Basically, any class where I have a lot of definitions, I use Quizlet on my phone. I set up the flashcards on the app so that if I'm like sitting somewhere and I'm bored, it's like, okay, let me just, do some quick studying of my I was doing this for 604 with Dr. Spetkov because we had like 100 definitions that we had to know. But that is kind of that's a good approach. That's what I would highly recommend. You're not going to have that many definitions in this class, but that would be what I would recommend. I guess any questions about any of that before we go forward? Anything that we're wondering about in terms of the structure, in terms of expectations, or anything like that? Awesome. Yeah. Yeah, like in general, I'm gonna try to focus it on like the last lecture or maybe the last two lectures, and like the current scope of the homework. So yeah, all right. So today we're gonna continue talking about one group diffusion. Last time we have, so far, we've only considered bare reactors. Today, we are going to look at multi-region systems. And if you have a multi-region system, there's going to be an interface from one region to another. So we're going to talk about the interface conditions we apply for a multi-region system. And we're basically going to apply what we have learned about one group diffusion to some new applications. We're going to look at computing critical volumes, critical masses, talk about this thing called the power peaking factor, and then we're going to learn more about doing one group diffusion, but for a system that has multiple regions instead of just one, like a bare reactor. So this is just kind of some review slides. Last time we derived the time-dependent one-group diffusion equation. We saw that it had a space component, that R1 of R, which is our fundamental mode flux shape. And it had this time component where lambda1 was the K eigenvalue. But we saw that we could rewrite that in terms of these properties called the buckling term. So that's the BG squared and the BM squared. This equation has time evolution. The evolution of our how our neutron population evolves with time will tell us something about the reactor state, like if it's critical or subcritical or supercritical. So in terms of like what we're showing here, these are the criticality conditions that we need to be able to know to describe a system. These are the three different ways in terms of the effective multiplication factor, in terms of our bucklings, and in terms of the K eigenvalue, how we can describe the state of our reactor. So if I ever said on a quiz, give me the three conditions for a critical reactor, that would be your answer. K equals 1, BM squared equals BG squared, and lambda 1 equals 0. Ideally, if our reactor is critical, those bucklings, this BM squared is the same as the BG squared. So we're trying to like set up a reactor so that the material and the geometric properties agree, and it allows us to make our system have a steady state neutron population. We defined this thing called BM squared, which was the material buckling. And that came from it's a material buckling. So it's only based on the material properties that appeared in the diffusion equation. And we introduced the definition of the diffusion length, which was the square root of D over sigma A. So those are some fundamental terms that we talked about last time. We went through the process of deriving this steady distribution for a sphere. We saw that the eigenvalue for that sphere was this pi squared over r. And we saw that the flux shape looked like 1 over r times the sine of pi little r over big R, where big R is the extrapolated radius. So this was a good table that I mentioned is useful. On your homework, you have a problem where you're deriving the flux shape and the BG squared for a cylinder. So this right here is going to be what the answer to that is. And on your homework, I also told you where in Spetkov's notes you can basically see that derivation. What I want us to do for that one is and I've set up the homework so that I'm helping you go through those like key steps to doing the process of finding that fundamental mode flux shape and the corresponding geometric buckling, which is the eigenvalue. So that's just kind of like a review of some of the things we talked about last time. I gave y'all this table that I said was useful too about the forms of the Laplacian and these other operators for our different coordinate systems. And we developed this fundamental definition for the reactor power, and we said that we can start with the definition of fission rate density, and then we can recognize that if the units of that are fissions per unit volume and per unit time, that the energy per fission, this E sub F, tells us about how much energy is released per fission. This is like a multiplier that we can add on to the fission rate density so that it converts our units from fissions into energy. So in this sense, this is the definition for the power density. It tells us about the how it's a distribution. So it basically tells us where in our reactor is the most power being produced and where is the least power being produced. And if you take this distribution, it's a power density, so it's power per unit volume. And if you integrate that over the whole volume, that'll give you the total reactor power. So this is a definition that is good to know because in that table with all of our fundamental mode flux shapes, the flux magnitude is a constant that we evaluate based on some characteristic of the reactor, like a reaction rate or a leakage rate, or the power. So this is how you can get that flux magnitude in terms of the reactor power. So a good quiz, maybe not a good quiz question, but certainly a good exam question would be to like ask you to derive these flux magnitudes for any of these simple geometries, right? So like I kind of showed y'all the steps to doing this for the sphere. I didn't actually show you how to carry out that integration, but it's integration by parts. If you have any trouble with that, definitely let me know. But that's something that if we were practicing and we were studying, these are good questions that I could give you on a test because you don't need a calculator to carry out most of these integrals. If I gave you if I gave you anything that involved the Bessel function, you would need a calculator for that. So that might not be as good for a derivation. But yeah, when we're seeing these things in class, good to make sure that we're familiar with them because those are good possible test questions. So in terms of getting started for today, I kind of wanted us to get some appreciation for just what that fission rate might be in a large nuclear reactor. So this is like a cross section, like a cutout of a model of the Westinghouse AP1000. That's like the most recent advanced reactor to be licensed and to be built in the United States. It's also like the newest generation, like I guess they call it 3+, because it has all these cool passive safety systems like if you ever look at the outside of the AP1000, the containment dome looks like it has this cool little hat on it, and that's because they actually store like a couple like swimming pools worth of water up here, so that if there ever is any accident where they lose power, they've got like a giant reservoir of water up top that they can dump onto the core to keep things cold. So whenever they say it's AP1000, that's like about a number for the electric power of the reactor. But there's thermodynamic efficiency. So like the actual energy being released is the thermal power, which is more like 3,400 megawatts. And then you have thermodynamic efficiencies, which means that if this is how much energy is released, I can never actually utilize that much. I'm going to lose some of it. So that corresponds to like about a 30% efficiency. So if the total like heat generated from the reactor is 3,400 megawatts, and we know that the energy per fission is 200 mega electron volts per fission, then if we take the ratio of those things, if we take the ratio of the thermal power to the energy per fission, that's going to give us a way that we can approximate the fission rate of our reactor. Because the thermal power is like the total amount of energy per unit time being produced. And then that is all coming from fission. And those fission reactions can constitute 200 mega electron volts per fission. So if you take that ratio and then do some unit conversions to convert, megawatts is joules per second, and a MeV is a unit of energy. It's just a very small amount of joules. But if we carry through all of these unit conversions with this equation, we can approximate the fission rate. And the fission rate is about 10 to the 20 fissions per second. So that's SI, or that's scientific notation. If you were to write that as a number, it's 1 followed by 20 zeros. So that in the AP 1000, that is about how many fissions per second are happening in the entire reactor. So that hopefully gives us some appreciation for just how like large these fission rates are. All of that energy is being generated where in the reactor? In the core, and then specifically what part of the core? Like if the core has control rods, and if the core has cladding, and if the core has just the fuel, right? It's generated all in the fuel. Once it's generated in the fuel, that heat will transfer to other places, but it all starts in the fuel where the fissions are happening. And that energy gets released in what kind of form? Heat, right? All of that energy is released in the form of heat. In the sense that, all of the kinetic energy of those particles basically instantly gets converted into heat. So we have been getting these flux shapes, which show how the flux in our reactor changes. And if it's a critical reactor, it doesn't change with time, but it does change with something. And what does it change with? The flux in our reactor? Change with position, right? We're writing these arguments as like phi of R. So if it's a critical reactor, it changes with position. And we know that we can compute the flux using like those fundamental mode flux shapes. But also if we wanted to compute the fission rate density, that would just be the macroscopic fission cross section times the flux. And so where is the flux going to peak in our reactor? At the center, right? At the reactor's center. And because we compute the fission rate density from the flux by just adding a multiplier on front, then wherever the flux peaks is also where the fission rate density is going to peak. And if that is where our flux peaks, that's where we have the most fissions. That's where fissions are releasing all this heat. Where do we think we're going to have the highest temperature? We're going to have the highest temperature at that same point, at the center. So at the center is where we have the highest temperature. And if you are building a reactor and the fuel gets so hot that it exceeds the melting point of the fuel, then congratulations, you just did a Chernobyl and we're all in big trouble. So anybody who's designing a reactor has to make sure that that fuel never exceeds or really even gets close to the fuel's melting point. And that's like a key design limitation of any reactor that you want to build. We use this quantity called the power peaking factor to describe the kind of most extreme case of like maximum power density in our core to the average conditions of our reactor. So this is the symbol that we use for the power peaking factor. By definition, it is the maximum power density, which is going to be at your hotspot, divided by the average power density. So we could say that we're using the symbol Q triple prime for the power density. So it is the maximum value of our power density divided by the average value of our power density. So we'll say Q triple prime with a overbar for average. So if I can find the maximum power density in my reactor, and then I can find the average power density, I can take the ratio of those and that'll tell me the power peaking factor for my reactor. And all of our critical reactors that we've talked about with those critical flux shapes, all of them have a standard power peaking factor that we can derive using this equation. So if I ask you to evaluate the maximum power of the maximum power density, we already said that the flux and the fission density peaks at the center. And we know, just going to go back real quick, that this is our equation for the power density, right? And we said that the flux peaks at the center at R equals 0, or depending on your geometry, like X, Y, Z might be 0, but at the geometric center of your reactor, that's where your flux is maximized. So if I evaluate this at R equals 0, that is my maximum power density. Evaluating power density at the center gives me the max. To get the average, that is an equation. it's a definition that if I'm taking the average of a distribution, the power density changes with position. So the average is 1 over the volume of my reactor, and then I'm integrating the power density over that volume. So I integrate over the volume and then I divide by the volume. In this case, that would be the definition of the average power density. Right? So that's how I get the numerator. I evaluate at the center. This is how I get the denominator. I carry out this integration. And then that'll give me a symbolic representation for the maximum power density. So if you look into Spekhov's notes, this table comes right from there, and this is showing what this right column is your power peaking factor. So if you carry out that definition for each of these reactor shapes, this is what you should get for the maximum power density. And I gave you a homework problem that has you derive a couple of these, so that's giving you guys practice doing that. Once I tell you about it in class, once I give it to you on a homework, better bet that that's something I could ask you on an exam. This one might be a little bit long for a quiz. And that's another thing to think about just strategically as a student. Like, I can't give you something that's going to take 2 pages on a quiz. But if something takes a couple lines, that's a lot easier for me to justify. I can make you guys do that in 5 minutes. So this is a good table to know. It comes from 5.4.1 in Dr. Spetkov's notes. So just a real quick backtracking to give us a way that we can have a kind of different way to calculate K effective. We had last class, we wrote the steady one group diffusion equation as a K eigenvalue problem. We rewrote it in terms of the Helmholtz equation, and we saw that this coefficient Bn squared could be written, if we were to write this equation and get the Laplacian by itself and group all of these other constants onto the flux term, this is what that constant would work out to be. And this gives us a relationship between the K eigenvalue and then our Bn, which is like our Helmholtz equation eigenvalue. So at K, the diffusion equation has the K eigenvalue. The Helmholtz equation has this Bn eigenvalue. And this equation says that whatever my Bn eigenvalue is, there's a corresponding K eigenvalue and vice versa. So if I take this equation, I could rearrange it to get Kn by itself. And if I were to do the algebra, I would get nu F sigma F over sigma A. And then that is all over 1 plus L squared Bn squared. All I've done is just algebraically isolated Kn and this equation to get right here. And then from that manipulation, I can identify this numerator as its own special quantity. If I have nu F, sigma F over sigma A, what quantity is that? K infinity, right? So that numerator is actually K infinity. And then in the bottom, I still have 1 plus L squared Bn squared. And what we know is that when I'm talking about the eigenvalue that corresponds to my fundamental mode flux shape, it's the smallest eigenvalue of the Helmholtz equation. It corresponds to n equals 1. So if n equals 1, my Bn becomes my Bg squared. And also if n equals 1, then my Kn becomes my fundamental mode K, which is K effective. So if you take this equation and let n equal 1, which means we're talking about our fundamental mode, then that means that K effective, as a definition, is just K infinity over 1 plus L squared Bg squared. Because when n equals 1, Kn becomes K infinity, and Bn becomes Bg. And then we can backtrack and rewrite this in terms of our nus and our sigmas. This would be nu F sigma F over sigma over sigma A. plus d VG squared. So kind of depending on what you have, this is how you can write and express the effective multiplication factor in terms of material properties. That's like your K infinity and your L, as well as your geometric properties, which is your VG squared. This equation only holds for a bare reactor surrounded by vacuum. But it's a fundamental equation that we can use for these kinds of problems. So that'll be a question.
To just the vector multiplication factor formula just for their or to pertain.
So I guess everything here is for a bare reactor. So yeah. Mhm. And so yeah, that's a good one to have in our back pocket. You'll be able to make use of this one on the homework, and I think it's like the last couple of problems. This will be a good one to know. And okay, so that's what I wanted to say about K effective. And we had already talked about the ways that our reactor, we can define the criticality state of our reactor, and we can define that in terms of the buckling terms. What do we know about our buckling terms if the reactor is critical? Yeah, Bm equals Bg squared. Bm squared equals Bg squared. And that's a really good fundamental equation to start with if you're analyzing some geometry that you suspect to be critical or you want to make it critical, because that is the criticality condition. And then for every geometry, we have a formula for Bg squared. So we'll know something about the right-hand side. And we have a formula for Bm squared too, because it's just based on material properties. So we can write this criticality condition, and then we can figure out the characteristics of our system that it would have to be to make that equation be true and therefore for the reactor to be critical. So Bg squared is all from your dimensions. Bm squared is all based on your materials. Bg squared is uniquely determined from the dimensions. So what that means is that if I give you, it means if I give you my dimensions, you can calculate Bg squared. And for the sphere and for the cube, if I give you Bg squared, you can also compute the dimensions because they're 1-to-1. If you know this, you automatically know that, and vice versa. So for these, there's only one length that's going to satisfy the equation. But if you have a different geometry, like a cylinder, just going to skip one slide ahead. If you write Bg squared for a cylinder, it looks like this. It part of it actually looks just like the sphere. You have a pi over r tilde squared term. But you have an extra term that comes from, oh crap, this is actually an h. So I guess it is slightly different, and it's maybe not good to think of them as being similar. So I take that back. But so you have one term that depends on the axial direction, which is the pi over h. And then this 2.405 over r tilde squared, that comes from the radial direction. So here, the Bg squared, if I give you Bg squared, there's an infinite number of h's and r's that could give you that corresponding Bg squared. So here, the dimensions will tell you about Bg squared, but Bg squared won't necessarily tell you about the dimensions. So if you have a finite cylinder and you want to find the critical dimensions, you actually have to do an optimization problem because this Bg can depend on two different quantities. But what you can do is you can write the criticality condition, which is that this Bg squared equals Bm squared. You can evaluate the left side using this definition, and then you can write the volume of your geometry, in this case, the volume of a cylinder. And you can use the volume definition along with Bg to write the volume just in terms of one quantity and the material buckle. So so basically instead of having the volume as a function of R and H, you'll use this definition so that the volume is expressed as just a function of one variable. And if you have volume expressed as a function of one variable, then you can do the standard like Calc 1 optimization process by which you take the derivative of the volume, set the derivative equal to 0, find the corresponding value of R or H that satisfies that equation, and then that will give you the minimum dimensions, the dimensions corresponding to your minimum volume, and then you can plug that back into your volume equation to say, well, you can plug it back into BG to say what the other dimension is. You can plug it back into the volume to say what the minimum critical volume is. So that's just kind of like the steps that you would go through. There's examples of this in the notes. There's also another method of doing it with the Lagrange multipliers. If you're comfortable with Lagrange multipliers, do it that way. I think the Calc 1 optimization problem method is more intuitive, and we have more practice with that. So like I'll never make you do something with the Lagrange multipliers, but if you want to use it, it's another method. So this is just a kind of helpful, these are the steps that you would go through if you want to try to do that optimization for a geometry where BG depends on multiple dimensions. And if you do some calculations to figure out what the minimum critical volume is, you start with BM squared equals BG squared. You rewrite everything in terms of the dimensions and BM. You can get these expressions and they will tell you what geometries have the minimum critical volume. We're expressing it purposefully so that the BM cubed is like a constant. Like if you have the same material properties for each reactor, then this BM cubed is going to be the same. And then we can see that it's based on the numerator here. If the denominators are the same, then which volume is minimum is going to be based just on the numerator. So we can see that the sphere has the smallest minimum critical volume, followed by a cylinder, and followed by a cube. So in general, to get a critical volume, the order is that a sphere is the smallest, and then the volume for a cylinder is the second smallest, and then the critical volume for a cube is the largest. So if you're given a reactor geometry and I'm giving you a cube and I say this cube is almost critical, it's got a K effective of like 0.99999. And then I say we take that cube and we smash it into the shape of a sphere. You have the same amount of mass and you converted it from one volume to another, that sphere would now be critical because you have the same amount of mass in a more critical volume. So that's one of the cool things about spheres is that they have, of the geometric shapes, they have the lowest surface to volume ratio. So that means that they basically experience less leakage, or to the extent that there is leakage, there's more volume than there is surface for things to leak out. Therefore, the sphere has the best critical volume. So if you have like minimum materials and you want to make a critical thing, sphere is your best geometry. The the composition matters too. So this is illustrating that plutonium-239 is going to get you a smaller critical mass than say uranium-235, and that's relating to the material properties of plutonium being better at like production over absorption. So these are good things to know about critical flux shapes, critical geometries. Sorry. So far, all we've talked about is one region reactors. But all real reactors are going to be multi-region. All real reactors are multi-region reactors. And when we say it's a multi-region reactor, it means kind of like what we see on this picture. It's not just fuel surrounded by vacuum, right? We've got control rods, we've probably got coolant, we've got some kind of structural materials, we've got like reactor shielding. In the reactor core itself, you might have some tubes where you have instrumentation, like you might have an in-core detector. So these reactors are have multi-regions. But what we can assume is that within every single region, like if I was just looking in this uranium fuel, we can pretty safely assume that within this uranium fuel, all of the uranium properties are the same. So within each region, we can say that material properties are uniform. material properties are uniform, that means we can treat them as constant within a region. Like if I have uranium fuel, I can use nu F and sigma A for that fuel. And at any point in that fuel, I can use the same material properties. But once I go from the uranium fuel to the control rod, can I use the same material properties? No, because they're a completely different material. So we allow them to vary from region to region. We allow them to vary between regions. And that actually makes things really nice for us because it means that all we have to do to solve a multi-region system is solve a bunch of one group diffusion equations for each region. So all we do is we solve the one group diffusion equation, solve the one group diffusion equation in each region, doing exactly what we did last lecture with like our critical sphere. And then once we solve it for each region, we match the solution that we get from one region to another. And the way that we force the solution in one region to match what happens, to match the solution. And when we say match, it's like the flux has to be continuous. So if I have like an inner core and then an outer core, the flux distribution can't have a discontinuity as I go from one region to another. And that means that I match the solutions in each region using an interface condition. So I'm going to do this using an interface condition. Let me rewrite that a little better. Condition. So that's all there is to multi-region systems, right? Solve one group diffusion in each separate region. Within that region, you can use constant properties. So it looks just like it looked when we did our bare reactors that were like homogeneous. And then we use these interface conditions to link the solution at each region. So this is a slide that's illustrating the multi-region reactor model. This is splitting the region up into it's a two-region problem. So I think it's more useful to look at this cross-section view. So V1 is the volume of region 1, V2 is the volume of region 2. And within each region, we have material properties that are the same in that region. So I'm following the same notation that Dr. Svetkov uses in his notes, where he uses a superscript to say that this is the material property in that specific region. So I would label one region as region 1, and then I would use the superscript to say, these are my properties in that region. And then I would do the exact same thing for region 2. And this horizontal line right here, that is the interface. That is the interface kind of surface between these two volumes. And at that surface, there is an interface condition that we are going to apply. Each volume has its own boundary, or at least each volume could have its own outer boundary, and that's where things might like be leaking out. That's also where we would specify our boundary conditions. And at this interface surface, there is an E hat n, which is the unit normal. It's the normal vector to the surface. It's at a 90-degree angle to my surface. So this is like kind of the picture that gives math meaning to the symbols that we use for a multi-region problem. And what I wanted us to do next is just start thinking about what our conditions would look like for this multi-region problem. So I've written the diffusion equation, the one group diffusion equation with a superscript I, where that I could be 1, 2, 3, and that's just saying however many regions I have, I'm going to have a diffusion equation for each region. Within each region, I have to have, I'm going to apply my boundary conditions, which says that if my region is for any part of my region that is near vacuum, like if it's um, concentric spheres and the outermost sphere is near vacuum, then at that outermost sphere, I would have to apply those vacuum boundary conditions. I'm going to need an initial condition that tells me for the entire reactor what the flux shape looks like at the beginning. And now, if it's a multi-region problem, I need these interface conditions, and these interface matches the solution from one region to another. So if I'm going from like a core into a reflector, the scalar flux is a continuous function, even if I go from one region to another. It can't have like a jump discontinuity or like any crazy like big any things that would make the function discontinuous. So the flux at region one, so flux at region one at my interface for all times has to be equal to the flux at the second interface, at that interface, at the position of the interface, and for all times. That's how we would write the continuity of the scalar flux. Flux in one region equals the flux in the other region at the region where they have an interface, and that has to hold for all times. So the flux has to be continuous, but also what has to be continuous is the current, which is kind of related to like the function has to be continuous, but it also can't have any like crazy kinks in the solution. And that would happen if you didn't conserve the current. We also conserve current, and that means it's the amount of current that's going through the interface. So if the interface has that unit normal, if we have that unit normal at the interface, if we take the dot product of that vector with the current in region one, also at the interface. So what this represents right here, this is the normal component of the current in region one, and the normal component of the current in region one has to equal the normal component of the current in region two. So this is going to have to be equal to E hat n at my surface, at my interface, dotted with J in the second region, evaluated at the interface. So that's mathematically how we can say that we are conserving the normal component of the current. And we're still doing diffusion theory. The main assumption that we've made in diffusion theory is that we're using Fick's law to represent the net current. So we can plug Fick's law into this equation and rewrite it using Fick's law. So just up here, J is minus D grad phi. That was our Fick's law. So we're substituting that into here. The D is a constant, so I'm just going to pull that out front. And the D for each region is going to have a subscript 1 for region 1 and a subscript 2 for, or sorry, superscript 1 and 2 for regions 1 and 2. So if I write this using Fick's law, it's going to look like minus D minus the diffusion coefficient in region 1 times E hat n at the interface. And now we're dotting with the gradient of the flux at the interface. Dotted with the gradient of the flux at the interface. So that's what this looks like if you rewrite the current using Fick's law. Oh, and I'm missing my 1 right here. That this is the flux in region 1. And on the right side, we'll have a very similar thing for region 2. So it'll look like minus the diffusion coefficient in region 2 times the E hat n at the interface, dotted with the gradient of the flux in region 2, evaluated at the interface. So those are the two new conditions that we get when we have a multi-region problem. We have continuity of the flux, and we have continuity of the normal component of the curve. But all the other conditions that we had for one group problems, one region problems are true. You've got a boundary condition, you've got initial conditions. You also have to have physical realizability in every part of your domain this has to be true about the flux. Your flux can never be negative, and it can never blow up to infinity. So that's our conditions. This is like all of the information we need to pose to have like a complete mathematical problem. And once you write all this down and you know what the Laplacian is for your geometry, you can start getting solutions to these kinds of problems. So what I wanted us to see is how we would approach this for a simple two-region reactor where it's concentric spheres. So it's like, like a gumball where you've got like, a bunch of different colors that are all, and if you were to take a slice, it would look kind of like the Earth, where you've got like all these different layers. So this is kind of like that. You've got an inner core, an inner sphere, which is our core made of fuel material. And then you've got an outer sphere, which is an infinite reflector. So we're saying that that reflector goes on for until to infinity. R at the interface, that's the radius of my inner core. And what we want to do is develop our steady one group diffusion problem for this geometry. So the first thing we're going to do is we're going to write the diffusion equation for each geometry and for each region. So here I've started by writing it for region 1, and I'm also specifying where region 1 is valid, right? Region 1 is defined from r equals 0 all the way up to the interface, but it doesn't include, a differential equation is never valid at the boundaries. It's only valid at the within the domain. So that's why I didn't include any equal signs here. This equation is valid from 0 to the interface, in between it, but not at those, not at the endpoints. And this quantity right here, nu f sigma f minus sigma a over d, all for region 1, we could rewrite that using a definition. What constant is that equal to? It's one of the bucklings. Are these geometric or material properties? So it's which one? Bm squared. Perfect. So I'm going to say bm squared and for region 1. So I'm putting the region in parentheses, hopefully to make it clear that that's not an exponent, that's just a identifier. So I've got a bm1 for region, bm squared for region 1. So that's what my equation looks like for the core. And then we want to write one group diffusion for the reflector. So I'm gonna just start writing what my diffusion equation looks like. So I've got the Laplacian in region 2 as a function of r, plus I've got this quantity right here. But in a reflector, does a reflector fission? No. So what's nu f and sigma f for a reflector? It's basically 0. So I'm going to just write minus sigma a for region 2 over d for region 2 times the flux in region 2 evaluated at r. Right? There's no sigma f, so we can just say here in the reflector sigma f equals, sorry, nu f equals sigma f equals 0 in the reflector. Right? Reflectors don't fission, so they have no sigma f or nu f. And what range of R values is the reflector, defines the domain of my reflector? R goes between what and what? R into infinity, perfect. We start at the interface, and it's an infinite reflector, so the reflector goes all the way to infinity. There's an important distinction between equation 1 and equation 2, the equation for region 1 and region 2, which is that here, if our medium is fissioning, what's going to be true is that nu f sigma f is got to be bigger than sigma a. Otherwise, our fuel doesn't actually produce more neutrons than it absorbs. So this whole quantity is positive if there's fuel in the reactor. But if there's no fuel in my region, and sigma f and nu f are 0, then I have minus sigma a over d, which is always going to be negative because I've got a minus sign up front. So if you have a non-producing region, you don't use BM. We could replace this with another constant so that it matches this form, but we're not going to call it BM squared. We're going to call it B effective. So this equation for the reflector looks like the Laplacian of phi2 evaluated at R minus B effective squared for region 2, and then that's multiplied by flux, and that whole thing is equal to 0. So if you have a non-producing region, you will use B effective instead of BM. It is still telling you, it's a similar, question?
Plus, is that also region 2?
Yes, thank you. Sorry, I missed my, good point. I missed my 2 right there. So yeah, it's still a buckling. It still physically represents the same kind of thing, but this is the material buckling just for a non-producing region. Because it's non-producing, we just call it something different. We call it B effect. So that's what my equations will look like for each region, and that's where they are valid. The next thing that we need to write is our interface conditions. So here, the interface is at R int. That means that we need to have the flux in region 1 evaluated at that interface has to be equal to the flux in region 2 also evaluated at that interface. The unit normal E hat n that points outward from our surface, from the so in this case, this is the interface surface. It's a sphere, but in 2D, it's a circle. Which way, any normal that I point, any outward unit normal, which way is that normal going to be pointing? Like, it's away from the center, right? Also, we could say if this is my E hat n, can't I say that this is pointing in the R direction? Because any direction outward is going to be in the R direction. So E hat n is E hat R. And in our, so that's what our unit normal looks like. It looks like E hat R. And if we write the Laplacian of phi in spherical coordinates, do we know what that's going to look like? If we don't, where would we go? Go to the table, right? So I'm going to go back to the table real quick. So we're looking for the gradient of the flux in spherical coordinates. Notice that's the gradient of the flux in spherical coordinates. It's just the derivative of the flux with respect to r multiplied by an E hat r, the unit normal in the r direction. So if I do, just keep that in mind. And ultimately what it means is that here, what we've got is, I'm going to write it right here. We've got, so the Laplacian of the flux dotted with E hat n. We just looked at the table, right? And we saw that this was d phi dr times E hat r. And we just said that E hat n in this problem was E hat r. So if I have E hat r dotted with itself, what is that going to give me? 1, right? Any unit vector dotted with itself is 1. So this whole quantity just looks like d phi dr. So when we're writing our interface condition for a sphere, what it's going to look like is just minus the diffusion coefficient in that region times the flux in that region with respect to r. In this case, it's that derivative is evaluated at the interface, and that's for region 1. So hopefully that makes sense how I'm rewriting that definition in terms of J, in terms of just what J actually would be for this geometry. So that's what it looks like on the for region 1. It looks like the exact same thing on region 2, but just with superscripts to identify that it's in region 2. So it's the diffusion coefficient in 2 times the derivative of the flux in region 2 with respect to R, also evaluated at the interface. And just to make it clear, it's at r equals little r equals r interface, little r equals r. Hopefully that's okay. And so now we have we have our equations spelled out for each region. We have our boundary conditions, our initial conditions, and our interface conditions, which were really the last thing that we needed. And in this case, because it's an infinite reflector, we don't really have a boundary condition because the boundary is infinite, but we still have physical conditions that have to be true. The flux still has to be finite. It can't blow up to infinity anywhere in our system, and it can't be negative. So this is the full problem statement with all of our conditions, and now we can start solving each equation separately. So the equations up top, that's what we had for region 1, and that's what we had for region 2. The geometry is a sphere, so we can rewrite these using the Laplacian in spherical coordinates. And if you don't know what the Laplacian in spherical coordinates is, we would go to the table. And we would see that in spherical coordinates, the Laplacian looks like this. 1 over r squared d by dr of r squared d phi dr. So that's what I'm replacing for the Laplacian in my equations. That's how I got here. And once I write these equations like this, now we need to think about, for differential equations that look like this, do we recognize their general solution? And hopefully we maybe recognize this one, because doesn't this equation look exactly like the 1D sphere that was bare that we saw last class? This is the exact same differential equation. It's going to have the exact same kind of fundamental solution form. This one in the denominator looks the exact same, but just the constant is negative instead of positive. And as it turns out, that constant does actually change what the general solution looks like. The next table I hope is useful because in engineering, we run across lots of differential equations. As you get more practice, you'll realize a lot of equations are in the same family. And once you can recognize their form, you know what their solution is going to be. And if it's anything more complicated than like doing it by hand, like we had on the test, on the quiz, where it was like it was a separable equation, or maybe you have to use an integrating factor. If it's any harder than that, then you basically have to know the solution and jump to it, or you have to like look it up in a book. These are like the most common equations that we will run into, and that's the corresponding general form, where if this plus or minus is just saying I could have a plus constant, I could have a minus constant. If the constant is positive, this is going to be my general solution, and if the constant is negative, this is going to be my general solution. So we're in 1D spherical coordinates. This is what our differential equation looks like. When it's a plus sign, it's a sum of sines and cosines with an r in the denominator. And if it looks like a minus sign, if we have a minus sign here, then it looks like a sum of exponentials. One exponential is positive, the other is negative, and then we pick up an r in the denominator. So like if you compare 1D slab to 1D spherical, notice that the general solution forms are almost the same. If it's a plus constant, it looks like a sine plus a cone sign in 1D slab. And if it's a minus, then it looks like a positive exponential and a negative exponential. If it's spherical, these solutions look the exact same. We just pick up an extra r in the denominator. That is kind of how I sometimes will remember these. If it's cylindrical, you end up with these Bessel functions, and it's harder to do analytically. Yes.
Just the negative in the 1D spherical on the cosine, that also supposed to be there, correct?
Oh, crap. No, that's a typo. Thank you for pointing that out. Here, let me just make that a plus sign. Yeah, please make a note of that in your notes. The sign doesn't change for the cosine and sine terms. It only changes on the exponential. Thank you for pointing that out. Oh, does anybody see any other mistakes on this term? Yeah, it should be an R, right? Sorry about that. Yeah, So B times R, B times R, B times R, B times so yeah, in this case, this is the table that we would want to take a look at. I think I would probably provide you, it would be a similar thing where like I would give you the insides of the table, but I wouldn't give you the outsides. Yes. I'm trying to think about it, and partly the reason I'm thinking about it is because I still have to make the exam. And I have to kind of make the exam before I know what the corresponding formula sheet is going to look like. Oh, well, that's the thing is that like I'm gonna make the formula sheet second because so that's partly I will try to get it to you at least a little bit before. I'll make a point to get it to you before, but I don't know how early before. You will see it before, so you'll have an idea about like this is what I have. Anything that like I feel like I might need to know extra that's outside of that, you would have some time to prepare. So moving ahead, right? If we recognize that those are the forms, that for phi one, it's going to look like a sine and a cosine, and for phi two, it's going to look like exponentials. Then the constant inside for region one is bm for one, and then the constant inside for region two is b effective for region two. And then there's four constants. So you have a C1 and C2 on the first term, you have a C3 and a C4 on the second term. Um, remember last time when we had this equation for the inner core region, when we looked at the solution for cosine of r over r, we saw that it blows up to infinity at r equals 0. So for physical realizability, if I plug in 0 into this equation, it's going to go to infinity, but my flux can't do that. So for physical realizability, that constant C2 has to be 0. That cosine term has to be eliminated from my solution. Otherwise, the solution will blow up to infinity at r equals 0. So because of physical realizability, I can eliminate this constant before I do any kind of extra work. So generally, like at r equals 0, that's where you can have funny business happening because of like a division by 0 or something blowing up to infinity. Same thing if you evaluate something at infinity. That's another place where things are liable to go to infinity if you're evaluating up to infinity. So this is the flux in region 2 in the reflector. If I were to plug infinity into this equation for r, which of those terms is going to go to infinity as r gets very, very large? The C3 term or the C4 term? Right? If you've got a e to a positive exponential, means if I make r very, very big, doesn't this whole thing go to infinity? And e to a negative exponential, if I make r very, very big, doesn't that go to 0? Which is exactly what I want for my reflector, that I can't have like an infinite flux at infinity, but it would certainly make sense that the flux drops to 0 as I go infinitely far away from my core region. So because of the conditions that we have, we can say that C3 has to be 0. So before we've even solved anything, we've already knocked out two constants. That makes our remaining constants C1 and C4. To find those constants, we have two constants and we have two interface conditions. So if we use those interface conditions kind of like boundary conditions, then we can make these two general forms fit those interface conditions. And generally, for every interface you have, you're going to have two constants to solve for. So if I gave you a 3-region system, you would have two interfaces, and therefore you would have 4 interface conditions and 4 constants. If I gave you anything more than 2 on an exam, it would be all symbolic. But so yeah, that in terms of like what is useful to ask, it probably wouldn't be much more than 2. Otherwise, it's all symbolic, and I can't really say like take the determinant or anything if it's like a giant matrix. I mean, I could do that, but I wouldn't do that because that would be mean. Okay, so once we knock out the constants that we don't care about, those are our solutions. And we have to make them obey our boundary conditions, right? So the first boundary condition says that this flux solution 1 in region 1 at the interface has to be equal to the flux solution in region 2 evaluated at the interface. So I'm just taking this expression and I'm evaluating it at the interface. And I'm taking this expression and I'm evaluating it at the interface. And then I've got the interface on the bottom, so I could like divide that out. And then I could take the term on the left side and move it over to, or sorry, the term on the right side, I could subtract it and move it over to the left side. And then this is my equation 1, where it's a constant times some number, right? If I know Bm, I can get this number. If I know the R at the interface, I know this number. Therefore, this sign of this thing is just a number. Same thing with this exponential term. That's also just a number. So this is one equation for my two constants. And if I apply my interface condition, that's how I can get another equation. So this right here is my interface condition. And here I'm spelling it out for this is what it looks like on the left side. And then this is what it looks like on the right side. So this is doing it for region 1, and this is for region 2. So basically I'm taking the derivative of this function, that's right here, and then I have a constant up front, and that's right here. This problem is actually shown in the notes, so I'm mostly walking through it so that we see what the like general steps are. I could show you how to take this derivative, but then we'd probably spend the next like 10 or 15 minutes just taking derivatives. I trust that if this is the function, and you know that if I take the derivative of it, I get this, that after class we could make sure that we could follow those steps if we needed to. But that's basically how I'm getting the left side and the right side. And then this left and right side are equal. So I'm setting them equal, but then I'm moving everything to one side. And so that's how I got this equation too. It's this term is equal to this term, and I'm moving everything over. And so here I see something pretty similar, which is that I've got one of my constants times a bunch of numbers, and then I've got my other constant also times a bunch of numbers. So equation 1 and equation 2 are actually just linear equations in the variables C1 and C2. So those were the two equations that we found. Those are linear equations in C1, sorry, yeah, C1. Shit, I'm messing up my terms now. It was a C1 and a C4. So whenever I say C1 and C2, that should be a 4. Apologies for that. Yeah, because look, I have a constant C1 and C4, and I have a C1 and a C4. So if I want to solve this system of equations, I could throw it into a matrix, and then I could do linear algebra stuff. Because if I write these equations in matrix form, notice that if I pull the C1 and the C4 out, then this would be my expression. And I made a typo here. I forgot to make sure we cancel him out, because what I'm doing here is I am showing how these two equations can be converted into a matrix form. If I wanted to go back from here to there, I could just multiply this out, right? I would do this term times C1, and I would do this term times C4, and then I would be right back up here, right? I would have C1 times this guy minus C4 times that. And if I were to distribute out the bottom, I would have this term multiplied by C1, which would give me that guy. And then I would have C4 multiplied by this term, which would give me that guy. So this is just writing the equation as a linear system of equations. Symbolically, it looks like I've got a 2 by 2. This thing right here is my 2 by 2 coefficient matrix, and it's being multiplied by a column vector, a constant column vector that has 2 elements. And that is equal to the 0 vector, which also has 2 elements. And if we think back to our certainly fun and enjoyable times in linear algebra, we recall that if you have a system like this, the only way for it to have non-trivial solutions is if the determinant of this 2x2 matrix is equal to 0. So once we get here, we just take the determinant and we set that determinant equal to 0, and that gives us a criticality condition or a criticality equation. So we are gonna take this determinant. And if I take the determinant of a 2x2, like operationally, what am I gonna end up doing? If it's an easy matrix like A, B, C, D, and then we take the determinant. Yeah, A, D minus B, C, right? It's like we cross multiply, but then we add a minus sign in the middle. So that's exactly what we're going to do here. We're going to multiply A times D, which is going to give me sine of BM1 times R at the interface. That's A. And then times D, which is this term down here. So I'm going to pull the D2 term up front. And then I've also got my exponential negative B effective in region 2 times the R at the interface, and then times my B effective in region 2 times R at the interface plus 1. That's my A times D term. And then I'm going to multiply the other two across, and I'm going to add them. So when I do that, I'm going to end up with just a plus sign, right? Because if I were to just multiply these two together, I've got a minus sign up front. So that whole thing would be negative, but I have to take the negative of that difference. So there's going to be basically two negatives that cancel each other out. And then this term is going to be D1. Oh, question?
That's C1.
Yes, thank you for reminding me. Yeah, that's the C1 that I crossed out on the original one, and then I copied my mistake because I just noticed that mistake this morning when I was reviewing. So yeah, that means that what's left here is a BM1 R at the interface times a cosine of BM1 times R at the interface minus the sine of BM1 times R at the interface. Close my big bracket. And then that is also being multiplied by this exponential term. So times exp of negative B effective in region 2 times the radius at the interface. And that is all equal to 0. So if I spell out all the terms, that's what it looks like when I take the determinant of a 2x2. Notice that both this term and this term have a common, well, there's a common exponential, the e to the negative b2 times r. So I could divide both sides by the exponential, and that's just going to cancel here, and it's going to cancel here. And then I've also got a sine here, and I've got a sine here, and I've got a cosine there. So if I were to divide by sine of BM1R interface, both sides by that sine function, this sine is going to cancel. I'm going to have sine of BM1 R interface divided by itself, which is just going to give me a 1. That's where this minus 1 comes from. And when I do cosine over sine, I get cotangent, and that's where this guy comes from. So if I divide by the sine function and the exponential, and then I just rearrange a little bit, I can get to this expression right here. And the part of the reason I've rearranged it like this is because the way that you would actually solve this equation is by plotting both sides and then seeing where they intersect each other. And by plotting it like this is a very fast varying function of the material properties and geometry, and that's a more slowly varying function. So it becomes easier to like find where they intersect. And that is how you would end up. This is the criticality condition. So if you find a combination of material properties that satisfy this equation, then you will have designed a critical reactor for this problem with an inner sphere and an infinite reflector. So that is that's what we would refer to as the criticality condition or the criticality equation for this multi-region reactor, right? If it's a multi-region reactor, it's not going to be as simple as like K effective equals this nice equation. We're going to have some complicated expression where we have to do probably using like a computer or doing some kind of numerical technique to figure out how we can pick our values of these constants so that this equation is true. So that's more or less everything that I wanted to say about the multi-region stuff. And then I just had a short aside on decay chains because that's another thing that is going to come up in it's going to come up in this class, and it's also come up probably in other classes. They're a good way to practice conservation, actually. So if you have a radioactive decay, this is like a very simple decay chain where you're starting with nuclide X and it is decaying. Lambda X is the decay constant for atom X. It's decaying into Y, and then Y is decaying into Z. So Y also has its own decay constant. Z we're assuming to be stable. So the chain kind of stops with Z. So lambda is I is the decay constant for whatever nuclide we're talking about. The decay constant has units of inverse time, so it's kind of telling you about the expected number of decays per unit time. So that's what the decay constant represents, and these governing differential equations are basically just saying the rate of change of this quantity of the amount of atoms of X is equal to all of the ways that the X could be being produced minus all the ways that we could be losing that atom X. So if this is some like fission product that's being born in our reactor, then we might have a production rate of that isotope. So that's what this Rx is. It's the number of atoms per second of atom X that are being produced. And we're just treating that as a constant. So this is growing because it's being produced, but it's radioactive. So it's also decaying. And as it decays, its amount goes down. And so this right here, this lambda times n, this is the decay rate for atom X. We can write these decay rates as a lambda times an n for that quantity. So every time X decays, it loses some of its material. In general, radioactive decay, it only depends on the constant, the decay constant, and how many atoms are there. If you have no atoms there, if Nx is 0, then you have no decays because you have nothing there to decay. But if you have a whole lot of that material, if N is very, very large, your decay rate is going to be large because you have a lot of stuff there to begin with, but it also depends on how fast it decays, which is the lambda. So in general, for any isotope, you can write its decay rate as a lambda for atom I. We can say that it is, I'll just say decay rate equals negative lambda I times n of I. So that's why for atom X, it has a production term and it has a loss term because of its decay. Let's think about atom Y now. This says rate of change of atom Y equals its gain rates minus its loss rates. So Y can be produced from a production term, Ry, but also every time X decays, it becomes Y. So whatever the decay rate is for atom X, this quantity, the number of atoms of X that are lost, becomes the number of atoms of Y that are gained if we're assuming that every decay of X gives us one Y. So Y in the middle of this chain has two gain terms. One because it could have a production rate, but also because X is decaying into Y and producing Y. But Y itself is also radioactive, so Y is also decaying into Z, and that's why we have a loss term for atom Y, which looks like its decay constant times its atom amount or atom density. And then Z is at the end of the chain, so it has no loss terms because it's stable. it only has gain terms because of production, and also similarly, every time y decays, it produces a z. So this right here is the governing differential equations that describe this condition. And these are the differential equations. Those would be possible initial conditions. And if you have the equation and its initial condition, you can solve each of these individual equations for the corresponding amount of the atom that's there. If you want to solve this one, you have to solve this one first, because notice the solution of this is going to be nx as a function of time. And in this expression right here, that nx as a function of time is right here, right? So if we want to solve this for ny, first we need to find what this nx solution is from the first equation, plug it into here, and then we've got an equation that we can solve for the unknown function ny. And I forgot that I wrote that down. But yeah, so that is just kind of an aside. If you look in, and I'll show you where in the Lamarche book to look. Because this is discussed. Partly why I asked this is that I look at that as almost like a good review question, because at least I remember covering that in other classes. If you need some like kind of extra review for that, if you go into resources, sorry, not the Lamarche book, it's in the Deuter. And I believe it's like one of the first things that's covered in chapter 2. So this is chapter 1, and chapter 1 is very short. But then when you get into chapter 2, nuclear reactions. Okay, yeah. So radioactive decay is the first nuclear reaction that's covered in the Duderstadt book, starting on page 12, end of 12, beginning of 13. So if we're looking at this, the stuff I was showing on the previous slide, and we're like, that's not enough, I need some more, this would be the thing that I would take a look at. Duderstadt pages like 12, 13, 14. Oh yeah, so right here's those decay chains. So yeah, 12, 13, 14 on Duderstadt would be a good one to review if we're fuzzy on the decay chain stuff. And that was the last thing that I had for y'all for today. So I finished a little early. I guess you're welcome, or maybe sorry, depending on how we feel. If y'all have any questions, feel free to let me know. I'll stay back for a little bit if y'all have any homework stuff that y'all are wondering about. Oh, let me pass back your quizzes too. Joshua Reed. Marion. Anne. Paxson. Oh, John Dykes. Bert. Bert Vaughn and okay, Bert's not here. Parson. Bob. King. The house. Mike. Tyler. John. Let's see. The last name is Ruffle, and I know it's you, but I see. Oh, yeah, Sandra? 2:30 to 7. Elizabeth? Yeah. Reactor. All right. If you didn't get one, it means I didn't get one from you. And If you have any questions on that, feel free to let me know. Those, hopefully, if we made mistakes, we can go back to the first like 2 lectures where we had all those definitions. And yeah, if there's questions about any of that, feel free to let me know. Thank y'all for your time. Have a good rest of your week and a good weekend, and I'll see y'all on Friday for the help session if you're gonna be there. Otherwise, I'll see you next week. I'll bring a treat. It might not be cookies. Y'all missed out on some really good cookies, by the way. Oh, I'm sorry. I gotcha. I understand. And that's partly why I'm recording them so that if you do happen to miss, I will. Yeah, for sure.
Can I get a copy of the quiz that we took today?
Oh, yeah.
Yeah.